A modern airliner's wing is an engineering marvel, designed to be both incredibly strong and surprisingly flexible. It's the structure that generates the lift to keep a 400-ton machine airborne. Yet inside this vital component, aerospace engineers store tens of thousands of gallons of highly flammable jet fuel. At first glance, this seems like an astonishingly dangerous choice. Placing the most volatile substance in what looks like the most exposed part of the plane feels like a disaster waiting to happen. But this design is no accident. In fact, it's one of aviation's smartest compromises. The placement that seems so risky is a key element of the aircraft's structural integrity, helping to reduce the immense forces that try to bend and break the wings in flight. This decision to store fuel in the wings wasn't an obvious one. In fact, if you look back at the early history of aviation, you'll find fuel tanks almost anywhere else. They were often placed in the fuselage, sometimes right behind the pilot, or in separate external pods bolted onto the aircraft. This approach made intuitive sense. Keep the flammable liquid in a dedicated, isolated container, away from the complex, load-bearing structures. But on a modern long-haul jet, the situation is radically different. We're not talking about a small tank. A Boeing 787 can carry over 36,000 gallons of jet fuel. That's more than 240,000 pounds, or 110 metric tons. To put that in perspective, the fuel alone can weigh more than 100 mid-size cars, and all of that massive, shifting weight is housed inside the two structures that are under the most intense aerodynamic and gravitational stress during flight, the wings. This creates a central paradox. Aerospace engineers, whose primary job is to manage risk and ensure structural integrity, deliberately moved away from the seemingly safer, isolated tanks. They chose to fill the very structures responsible for keeping the plane in the air with a volatile, flammable liquid. It seems to fly in the face of common sense, adding a huge potential hazard to the most critical part of the airframe. The easy answer is that wings simply offer a large, unused volume. And while that's true, turning a wing into a fuel tank is an immense engineering challenge. It's not just an empty box. It must be meticulously sealed, with thousands of rivets and joints made fuel-tight. The structure has to be designed to contain this liquid mass while flexing and bending in turbulence. This wasn't a decision of convenience. It was a fundamental shift in aircraft design. So, was this choice really just about saving space? Or did engineers discover something profound about the physics of flight that made this dangerous idea a brilliant one? The answer lies in a concept that aerospace engineers call a wet wing. This is a crucial distinction. There aren't separate container-like tanks placed inside the wings. Instead, the wing's own internal structure is engineered to become the tank itself. In simplified terms, the strong internal framework of the wing, the spars that run lengthwise, the ribs that give it shape, and the metal skin that covers it all, is sealed to form a fuel-tight vessel. This is an incredibly demanding engineering feat. A modern wing is assembled from thousands of individual parts, held together by tens of thousands of rivets. To turn this complex structure into a leak-proof container, every single joint, seam, and rivet head on the inside must be coated with a specialized polymer sealant. This sealant has to be durable enough to withstand constant contact with jet fuel, yet flexible enough to move and stretch as the wing flexes in flight, all without cracking or failing. The primary advantage of this approach is immense efficiency. Building dedicated bladder tanks or rigid containers to fit inside the complex, tapering shape of a wing would add a huge amount of weight and complexity. Those tanks would be heavy, and their shape would mean that valuable space inside the wing goes unused. By making the wing's own structure do double duty, providing lift and containing fuel, engineers eliminate the weight of separate tanks entirely. This allows the aircraft to carry more fuel for a given weight, increasing its range, or carry the same amount of fuel while being lighter and more fuel efficient. So, the wet wing is a masterclass in structural and volumetric efficiency. It solves the problem of where to put all that fuel without adding unnecessary weight. But this solution seems to create an even bigger problem. We now have a massive amount of weight distributed far out along the wings, pulling them down. Shouldn't this put an unimaginable bending force on the wing roots, threatening to break them? The truth is the exact opposite, and it reveals one of the most elegant principles in all of aerospace engineering. To understand why, you have to visualize the immense, invisible forces at war on an aircraft in flight. The first force is lift. It's generated across the entire length of the wings, pushing them upwards with a force equal to the entire weight of the aircraft. Hundreds of tons pushing relentlessly toward the sky. The second force is gravity, pulling the massive weight of the fuselage, passengers, and cargo straight down. This creates a colossal bending moment at the wing root, the point where the wing joins the fuselage. In simplified terms, the lift is trying to fold the wings upward, while the fuselage is trying to tear them downward. Without any countermeasure, the wing structure would have to be incredibly heavy and thick at the root to resist being snapped off. This is where the fuel's location becomes a stroke of genius. The weight of the fuel, distributed all along the wing's interior, creates its own downward force. This force directly counteracts the upward push of lift, right where it's being generated. Aerospace engineers call this bending relief. The fuel isn't just passive cargo. Its weight actively works to flatten the wing and reduce the stress on the wing root. Think of it this way. It's much harder to carry a single 80-pound backpack than it is to carry two 40-pound suitcases, one in each hand. With the backpack, all the strain is concentrated on your spine. With the suitcases, the weight in your hands helps balance the load across your body. On an airplane, the fuselage is the backpack, and the fuel in the wings acts like the suitcases, relieving the structural strain. One major advantage is that this allows engineers to design wings that are significantly lighter and more structurally efficient, which in turn saves fuel and increases range. The fuel's weight, therefore, is not just dead weight. It's an active structural component that helps the wing do its job. It's a brilliant piece of engineering. But this raises a new, critical question. A long-haul flight can burn off nearly half of its initial weight, meaning tens of tons of this helpful counterweight disappear. As the fuel is consumed, doesn't this create a constantly shifting balance issue? A new and dangerous dynamic problem that could threaten the stability of the entire aircraft? Yes, that is a critical problem. As tons of fuel are burned away, the very weight that provides that helpful bending relief vanishes. This constant shift in mass could create a catastrophic balancing issue. And the solution to this problem reveals another layer of engineering genius: active flight management. For any aircraft to fly safely, its weight must be precisely balanced around a single point, called the center of gravity, or CG. If the CG shifts too far forward or backward, the plane can become dangerously unstable and difficult or even impossible to control. This is where the location of the fuel provides yet another major advantage. The wings are located very close to the aircraft's center of lift, the average point where the upward aerodynamic force is applied. By placing the fuel here, its weight is already centered near the aircraft's natural balance point. As the fuel is consumed, the overall center of gravity shifts far less than it would if the fuel were stored in a single, massive tank in the front or back of the fuselage. But engineers don't leave this to chance. The wing is not just one giant bathtub of fuel. It is subdivided into multiple interconnected tanks, typically a center tank in the fuselage between the wings, and main tanks within each wing structure. Throughout the flight, a sophisticated and highly automated fuel management system, consisting of computers, pumps, and valves, is constantly at work. It transfers fuel between these tanks according to a precise sequence. The primary goal is to maintain the optimal center of gravity, ensuring the aircraft remains perfectly balanced from takeoff to landing. The exact design depends on the aircraft type, but the principle is the same. The aircraft is actively managing its own balance in real time. This also helps explain engine placement. While fuel proximity is a small consideration, the main reasons engines are slung under the wings are structural efficiency, easier maintenance, and better airflow. It's another complex set of engineering trade-offs. So, engineers have transformed the fuel from a simple payload into a key part of both the aircraft's structure and its dynamic balancing system. It's an incredibly smart design. But this brings us back to the most visceral, unavoidable fear. We have flammable fuel, complex electrical systems, and powerful engines all located in the same general area. How can a design that clusters all these potential hazards together possibly be considered the safest option? The solution to placing fuel in the wings, therefore, isn't just one good idea. It's a single, elegant answer to multiple, competing engineering problems. It is the grand compromise of aircraft design. First, the wet wing offers unmatched volumetric efficiency, creating the largest possible fuel tank for the lowest possible structural weight. Second, the fuel's mass provides critical bending relief, actively reducing the immense strain on the wings and allowing for a lighter, more resilient airframe. And third, its location near the center of lift, combined with an active management system, ensures the aircraft remains perfectly stable and controllable from takeoff to landing. But this entire system rests on the ability to manage the inherent danger. And this is where aerospace engineers have built in layers of defense. The wing is already one of the most over-engineered and structurally redundant parts of the aircraft. But the most critical safety feature is invisible. To start a fire, you need fuel vapor, an ignition source, and oxygen. Engineers decided the most effective strategy was to eliminate the oxygen. Modern airliners use a fuel tank inerting system. This onboard system filters nitrogen from the air and continuously pumps it into the fuel tanks as fuel is consumed. This displaces the oxygen, creating an inert atmosphere inside the tank where a fire simply cannot start. Furthermore, in the event of a survivable crash, the wing's location provides a crucial safety advantage. It keeps the vast majority of the flammable liquid away from the passenger cabin and emergency exit paths, increasing the time available for a safe evacuation. What appears to be a dangerous flaw is in fact one of aviation's most intelligent and holistic solutions. The exact design depends on the aircraft type, but the underlying principles are universal. The fuel inside an airplane's wing is not a bomb waiting to go off. It is a brilliant example of integrated engineering, where a single choice solves problems of space, weight, structure, and stability all at once. It proves that in the world of high-stakes design, the safest and most efficient solution is often the one that seems the most counterintuitive, born from a deep understanding of physics and a mastery of compromise.